This is the Power Technology Network. This course is an introduction to the well-known op-amp. It is used in many different applications, and most engineers have a good high-level understanding of it. But to get the most from an op-amp and to be able to select the correct one for an application, more in-depth application-level knowledge is required. This course is about providing this in-depth application knowledge. Before we proceed with the course, we must look at what is required to make the most of this course. The prerequisites for this module are: first, the student should have a working understanding of Bode diagrams. Bode diagrams are used to display the amplitude and phase response of circuits. Second, we recommend that the student have a working knowledge of LTspice, which is a well-known and popular circuit simulation package. LTspice is free. Third, the student should have a basic understanding of the op-amp and its characteristics. This slide is an overview of the course. At the start of this course, it must be said that this course refers to the op-amp, but the content applies to any amplifier. The characteristics and modeling taught in this course applies to any amplifier. We start with the theory of the op-amp. Then we present the tools and resources that are available to the student to simulate and experiment with the op-amp integrator. Next, we introduce the student to the components, such as the various make and model of op-amps, as well as the passive components, such as resistors and capacitors used with the op-amp. We show the student some practical design examples, and we provide the student with design assignments. Then we take the student through some of the practical aspects of op-amp circuit design. The theory will help the student build an understanding of the op-amp integrator circuit. The theory is presented in such a way that it helps the student build a conceptual model of the op-amp. The conceptual model is easy to understand and remember. This means that the student can use it anywhere, such as while the student is experimenting with the workbench circuit. At the end of the theoretical section, the student should have an intuitive understanding of the op-amp integrator circuit. The tools and resources include the simulation work using LTspice. This simulation work reinforces the understanding established during the theoretical section. The simulation work gives the student the chance to use the conceptual model developed during the theoretical section. It also introduces the student to the what-if analysis. By this we mean the student asks questions about what would happen if the circuit is modified, or component values are changed. The simulation software is the ideal tool for answering these questions. It also builds the student's understanding of the circuit. The student is introduced to some of the vast collection of material online, such as books, PDF documents from op-amp manufacturers as well as online videos. Selecting the right components for a circuit requires an understanding of the effect that the component's characteristics has on the performance of the circuit. Another aspect to consider when it comes to components is the package or footprint that the component comes in. The student is shown the various component packages available. The student is shown how to determine the component requirements for the op-amp integrator circuit. With this information, the student can compare and select the right components. There are several learning goals in this course. In this slide we shall go through these learning goals. Our first goal is to help you develop a fundamental understanding of the operational amplifier. This includes starting with the ideal op-amp, and develop an understanding of how it works. From here, we move on to a more practical understanding of the op-amp. But the real op-amps are not the same as the ideal op-amp. We introduce the student to the characteristics of non-ideal or real op-amps, and compare that with the ideal op-amp. In this course we make extensive use of LTspice to develop a step-by-step behavioral op-amp model. This develops the student's understanding of the op-amp characteristics and parameters. We also provide the student with generic LTspice op-amp models with parameter settings that can be used to simulate real op-amps. Topics such as closed-loop control, stability and compensation with capacitive load is also presented and simulated. We also take the student through a high-level view of the internal op-amp transistor circuit. This is only a high-level view so that the student can get a working understanding of the internal op-amp circuitry. We introduce the student to what op-amps are commercially available. This includes the various types of op-amps, various types of output stages as well as different manufacturers. We also guide the student through the various op-amp characteristics and parameters, and how to make design decisions and select the correct op-amp for an application. Just a general note regarding this course. We follow an approach of repeating and reviewing. The same concept is presented more than once, but using a different approach every time. The process of repeating drives home the concept. We also introduce regular reviews to further drive the understanding of the concept. The course starts by introducing the op-amp to the student. The analysis starts with the open-loop behavior of the op-amp, and it treats the op-amp as a black box with inputs and outputs. This model has two signal ports, namely an input and output signal port, as well as a third power port. First is the non-inverting amplifier, that has a positive gain, which is shown here. It directly amplifies the input signal by multiplying it with the gain. Second is the inverting amplifier, that has a negative gain. It amplifies the input signal by a negative gain, and therefore it is known as an inverting amplifier. These basic models are used to characterize the open-loop behavior of the op-amp in this course. This slide shows the open-loop behavior of the non-inverting op-amp in a bit more detail. Let's assume that the input signal is a sinusoidal voltage with a peak amplitude of 1 volt, as shown here. And let's assume the amplifier gain is 10. Then the output is also a sinusoidal voltage with an amplitude of 10 volts, as shown here. This slide shows the inverting amplifier, where the previous slide showed the non-inverting amplifier operation. Like in the previous slide, the input signal is the same, a sinusoidal voltage with a peak of 1 volt. Because the amplifier is an inverting amplifier, the gain is -10. The output voltage is again 10 times the input voltage, with a peak amplitude of 10 volts, but the output is 180 degrees out of phase with the input, because the gain is negative. For any amplifier, the output voltage is equal to the gain, multiplied by the difference between the voltages at the positive and negative terminals of the amplifier. This leads us to a simple graphical classification of the 4 different amplifier configurations, 2 for the inverting and 2 for the non-inverting amplifiers. And this is what it looks like in a 4-quadrant diagram. The non-inverting amplifier operation is shown in the first and third quadrants. In the case of a non-inverting amplifier, the input and output voltages are in phase. In the first quadrant the input and output are both positive, and in the third quadrant they are both negative. The inverting amplifier operation is shown in the second and fourth quadrants. In the case of an inverting amplifier, the input and output voltages are 180 degrees out of phase. In the second quadrant the input is negative, and output is positive. In the third quadrant the situation is reversed, with the input voltage positive and the output negative. We start with the first quadrant, where both the input and output voltages are positive. This is a non-inverting amplifier. The input voltage polarity is positive, and it is applied to the positive input terminal of the amplifier. The negative input terminal of the amplifier is grounded, and it is common between the input and output of the amplifier. This is a non-inverting configuration, because the output voltage is in phase with the input voltage. Next, we move over to the second quadrant. This is an inverting amplifier. Here the input voltage is negative, and the output voltage is positive. The input voltage is negative because polarity is reversed, with the positive terminal of the input source grounded and the negative terminal of the input connected to the negative terminal of the amplifier. The output voltage is the inverse of the input voltage. The reason for this is because the gain of the amplifier is negative. The gain is negative because the input voltage is applied to the negative terminal of the amplifier. And the input voltage is negative, because the positive terminal is grounded and the voltage at the negative of the input voltage source is taken as the output. A negative input voltage with a negative amplifier generates a positive voltage at the output of the amplifier, as shown. In the third quadrant we have another non-inverting amplifier, with the input and output voltages both negative. The input voltage source has the same polarity as in the second quadrant, with the output taken from the negative terminal and the positive terminal grounded. But the gain of the amplifier is positive, because the input voltage is applied to the positive terminal of the amplifier. A negative input voltage, therefore, generates a negative and in-phase voltage at the output. Finally, in the fourth quadrant we have an inverting amplifier again. The input voltage is applied to the negative terminal of the amplifier, making the amplifier gain negative. With the input voltage positive and the amplifier gain negative, the output voltage is negative. We start with the behavioral model for the ideal op-amp, which is shown here. As we already said earlier, like everything presented here, this model applies to any amplifier. The characteristics of this model are the following. The input impedance is infinite, which means that the voltage across the two input terminals is zero, and therefore the input current is also zero. On the output side, the output impedance is zero and the amplifier gain is infinite. As we shall see later, this model is useful in making a first-order analysis of an op-amp circuit, but more detailed modeling is required to do an in-depth analysis. In this course, we shall explore all these non-ideal aspects of an op-amp, or any amplifier in general for that matter, and add them to this idealized model. In this slide we use the model shown in the previous slide, and we develop the transfer characteristics for it, or the relationship between the input and output voltage. We start with the inverting amplifier, and in the next slide we do the same for the non-inverting amplifier. What we want to do is plot the relationship between the input of output voltages for an inverting amplifier on a graph as shown here. The input voltage is shown along the x-axis and the output along the y-axis. For the inverting amplifier, the transfer characteristics looks like this. The output voltage is limited to the supply rails at positive and negative limits on the y-axis. The input voltage varies within a narrow range on the x-axis, while the output voltage varies over a much wider range on the y-axis. This is because the output voltage is an amplified version of the input voltage. The gain is negative for an inverting amplifier, because the gradient of the line is from top left to bottom right. As already shown in a previous slide, an amplifier is an inverting amplifier when the signal is applied to the negative terminal of the amplifier, and the positive terminal is grounded, making the positive terminal common to both the input and output circuits of the amplifier. Using the model the previous slide, and with a negative input voltage, meaning that the negative terminal of the input voltage source is connected to the negative input of the amplifier, the operation is in the second quadrant. The amplifier gain is positive, because the negative terminal of the amplifier is used as the input terminal, and the input voltage is negative, therefore the output is positive. The input voltage varies in the negative range shown here. The output is clipped to the positive rail voltage. When the positive terminal of the input voltage source is connected to the negative terminal of the amplifier input, the gain is negative and the input voltage is positive, making the output voltage negative, as shown in the fourth quadrant. The operation is in the fourth quadrant, and the input voltages ranges along the x-axis as shown with the output voltage ranging from 0 to the negative supply rail. It is worth noting that this representation is linear, meaning that the line is a straight line until it ends in the supply rails. In real life, this curve is not always linear, and the graph is not a straight line, making it nonlinear. This leads to distortion and the input is not an exact amplified representation of the input. When this curve is not a straight line, it means that the gain is not constant, but varies. As we shall show later, this effect can be minimized using feedback. This variation of the gain can occur as a function of various factors, as component values varies with current. The gain or slope of the graph can also drift over time, for example, due to temperature. In this slide, we explore the transfer characteristic of a non-inverting amplifier, in the same way that we did for the inverting amplifier in the previous slide. We plot the relationship between the input of output voltages for a non-inverting amplifier on a graph as shown here. The input voltage is shown along the x-axis and the output along the y-axis. For the non-inverting amplifier, the transfer characteristics looks like this. The output voltage is limited to the supply rails at positive and negative limits on the y-axis. The input voltage varies within a narrow range on the x-axis, while the output voltage varies over a much wider range on the y-axis. This is because the output voltage is an amplified version of the input voltage. The gain is positive for a non-inverting amplifier, because the gradient of the line is from bottom left to top right. As already shown in a previous slide, an amplifier is a non-inverting amplifier when the signal is applied to the positive terminal of the amplifier, and the negative terminal is grounded, making the negative terminal of the amplifier common to both the input and output circuits. Using the model from a previous slide, and with a negative input voltage, meaning that the negative terminal of the input voltage source is connected to the positive input of the amplifier, the operation is in the third quadrant. The amplifier gain is positive, because the positive terminal of the amplifier is used as the input terminal, and the input voltage is negative, therefore the output is negative. The input voltage varies in the negative range shown here. The output is clipped to the negative rail voltage. When the positive terminal of the input voltage source is connected to the positive terminal of the amplifier input, the gain is positive and the input voltage is positive, making the output voltage positive, as shown in the first quadrant. The operation is in the first quadrant, and the input voltages ranges along the x-axis, as shown with the output voltage ranging from 0 to the positive supply rail. In this course we are systematically going to develop an equivalent circuit or behavioral model for the op-amp, and amplifiers in general. The result can be used to simulate the behavior of real op-amps, or amplifiers in general, by setting the equivalent circuit parameters accordingly. We start with the ideal op-amp model, that we already introduced in an earlier slide. And we add various real-world op-amp parameters, to make this ideal model more representative. We change the ideal model that has an infinite bandwidth, to a more realistic finite bandwidth. We add feedback and compensation, and analyze the effect of this on overall amplifier behavior. Then we add output clipping. The ideal op-amp output can reach any voltage, which is not realistic. In the case of an actual op-amp, the output is clipped to the power supply rail voltages. We also add slew rate to the output, which means we limit the rate at which the output voltage can change. We add input offset and input bias current to our model, to model the op-amp more accurately. Then we introduce common mode rejection to our model. Finally, we add power supply rejection to the model. And in the end, we have a model like the one shown in this schematic. In this course, we introduce the student to some tools and resources on op-amps. LTspice is used extensively throughout this course. It is a free, online circuit simulation application. It is well supported and there are many online resources available. Analog devices took over linear technologies. Linear technologies created LTspice and it continues under analog devices with regular updates and extensive libraries. Obviously, the library updates from analog devices focus on their products, but there are models available for LTspice from most of the large integrated circuit manufacturers. Building your own LTspice models is also easy, as you will see in this course. We build an op-amp model from scratch using LTspice. This model can be used to simulate various levels of complexity of op-amp models. We also use LTspice to simulate a simple op-amp internal transistor circuit. Finally, we use LTspice to simulate closed-loop amplifier circuits with feedback. We use LTspice to simulate the frequency response as well as the time response with varying parameter values. When it comes to real op-amps, it is easy to be overwhelmed with the sheer number of op-amps that are available. This includes many different suppliers, different types of op-amps as well as a whole list of op-amp parameters. For any application there are quite a few options. To make a decision about which op-amp to use, requires some guidance. Not everyone that uses op-amps are experts on the subject. However, it is necessary to know enough to select the correct op-amp. We provide a list of key op-amp characteristics and parameters to consider. We then show the student how to use the generic models we provide in a simulation. All of this helps with the selection of the correct op-amp. Before spending time to do this course, one has to understand why it is useful to do this course on op-amps. Everyone might have their own motivation to learn about op-amps, but here are some reasons and background why op-amp knowledge is useful and even valuable. Despite the digital revolution, replacing much of the analog circuits with digital circuits, op-amps are still prevalent throughout the industry. New op-amps, with better performance, are still being designed and the performance is continually improved. New types of op-amps are also being developed, like the chopper amplifier. This means that there are still companies willing to invest into op-amp technology, and that only happens if there is a strong demand for them. So, the question remains, why learn about op-amps? It is all good and well if there are companies developing them and there is a strong demand, but what use is it for a circuit designer to learn about op-amps? Well, first, as you will see in the rest of the course, they are very useful components that can be used to solve many interface and analog signal condition problems. And analog computing may even make a comeback with artificial intelligence. Op-amps are used whenever you need to amplify very small signals, for example signals in the microvolt range.
These signals are found in strain gauges, biomedical sensors, such as EEG, and ECG, as well as current shuts and thermocouples.
Op-amps are also used for level shifting, where bipolar signals are converted to single voltage levels, so that these signals can be fed into analog to digital converters, that pass this signal on to microprocessors. It seems that even the digital revolution requires a lot of analog signal conditioning. So, it is a valuable skill to understand how op-amps work. This is the end of the introduction to the course. Next, we are going to jump right in with the non-inverting op-amp.